Perfect. Thank you.
And our last speaker for today is Rob. And so he is telling us something about hybrid systems and long-range spin systems. Please.
Thanks a lot. Well, let me start by saying, as the last speaker, I have the pleasure of saying that at the end of this conference week, it has been really, really good. Lots of great conversations, lots of great talks. And maybe we should first start by thanking the organizers for such a great week. And hopefully, thanks a lot for everything. All right, well, with that behind us, let me talk to you about hybrid systems and long-range spin chains. So hybrid systems, the word that is maybe the most new here on this slide, is it's a system that's a dynamical system which is a little bit quantum and a little bit classical at the same time. And it will appear naturally from considerations in long-range spin chains. This is the conclusion of a bunch of work I've done with these collaborators. So to see if this works, I've clicked, but does it do something? Not yet. Now it works. All right, thanks. So the big overarching picture for me is that there's two realms of quantum integrability. The realm that you know probably the best is the one on the left, which is short-range integrability with the ubiquitous Heisenberg spin chain as its most canonical example. And we see it all over physics because it's very simple and it's very useful for all kinds of approximations. But sometimes it's a bit too simple of an approximation and you need to do a little bit better. So sometimes you come up with something like a long-range interacting spin chain like the Halding-Shastry spin chain on the right. This is already very different because you can see that it has pair interactions between every pair of particles. You have to fine-tune the potential very precisely to make sure that this is still integrable. And this is, for example, a much better model for things like the fractional quantum Hall effect, ballistic transport, and nanographene. Actually, the ballistic transport I learned about this week at the TU in Wrocław, which is very cool. So in general, both of these are quantum integrable in a very particular way. So quantum integrability is representation theory of quantum groups and algebras, and I'm going to just stick to Yangians for simplicity. So the quantum integrability of the Heisenberg chain basically is because we take a physical space, some tensor space V for every particle, so V to the power n. I add an auxiliary space to it, and then on this space, I have a representation of a Yangian. Then I have basically, well, the center of this representation, so the elements that commute with everything else, in this case has nothing, there's just only the identity. And to find my Hamiltonians, I take the trace of the monodromy matrix. This is a well-known procedure. You've probably all done this computation yourself. And if I want to create more states, I use raising and lowering operators, which I find from the off-diagonal pieces of the monodromy matrix. But long-range integrability works differently. So I still have a representation of the Yangian, but instead of having an auxiliary space, I add this extra complicated space, polynomials in extra variables x1 to xn. In this case, the center is not empty, so if I take the quantum determinant of the monodromy matrix, I actually get Hamiltonians which commute already between themselves, but they commute with everything in the whole thing, which means that if I find further elements of the monodromy matrix, these will actually be symmetries of my system. So I get very, very degenerate systems. But this also means I've now used all of my normal machinery, and if I want to raise or lower states, I need to find them somewhere else. So I can do this by looking at something more general like a toroidal algebra, and in this case, the generation which is called the affine Yangian. So these are two very different ways of doing representation theory, and the big thing I want to try is to find a way to bridge the gap between these two different things. So you can do this for concrete models, like the models in this picture, and maybe a small surprise for those of you who have never seen it, is that in the middle, I have elliptic models in the sense that these models have pair potentials which are elliptic functions, and this doesn't bring me further away from Heisenberg, it actually brings me closer. But this is still a bridge that is built out of spin chains. And really, if you look carefully at this space that I gave you on the previous slide, this representation theory for long-range integrability takes place on this particular space. So this is not just spins, but every particle in this representation also carries a position. So if you think about it a bit longer, this turns out to be a quantum many-body system with spins. And a canonical example of this would be the trigonometric spin Colodero settlement model. for which I've written down the Hamiltonian. And the picture is this. I have particles that can move, and they interact with their spins. And I have to figure out the integrability of that. But if I want to use this bridge that I showed you on the previous slide, I first have to figure out how do I get from this quantum many-body system down to a spin chain. So this goes through a trick that Polychronakos came up in the 90s known as freezing. Now, freezing is a very simple idea. It is just saying, I have these moving particles, I want to make them stop. I just set the temperature of my system to 0. Or equivalently, I set the coupling constant to infinity. Well, this is nice. And then you hope that your particles settle in an equilibrium somehow, and then you can just evaluate the whole system on that equilibrium, and it simplifies, and you have a spin chain left. But this is quite, I mean, it's intuitively clear, but mathematically there's lots of unknowns here. For example, which equilibrium am I supposed to take if there's multiple ones? Which model am I even supposed to take classical equilibria of? And there are clear cases where this doesn't work, like the elliptic case. And finally, yes, it's nice, it's a clear picture, but there's not really a good mathematical description of this limit in the sense that I can use this procedure to really transport my properties from the quantum many-body system down to the spin chain. So that's what I want. So this map, I want to reformulate freezing, we'll see, as a classical limit in such a way that I get a much nicer mathematical grasp on this whole process. Okay? So what is my setup? I take n particles like before. They have coordinates, they have momenta, and they have some extra degrees of freedom, which I will call spin, but please, yeah, please. Yes. I would say that these two things are not the same, clearly. But we'll see that the classical limit is the thing you should be doing in the end. But yeah, I think that's a very good question. So I have a system which has further degrees of freedom, which I will call spin, but please think of your own systems where you have some coupling constant, where you have maybe other degrees of freedom that you might use. And then I have a Hamiltonian, which at lowest order in my coupling constant h bar does not depend on these spins. It doesn't probe the spins at all. And then at first order in h bar, this is where everything starts to come together. And if you want to think of a kind of simple physical idea behind it, this is the Born-Oppenheimer approximation of heavy nuclei with very light electrons moving around them. Now you can do two things. The first thing you could try to do is get rid of all of your quantum stuff. That's what Larissa did for us on Monday, if you were already there. And then you get classical dynamics, which was mostly talk about geometry because it was classical. What I'm going to do is the opposite thing. I want to get rid of my classical stuff. So I keep my quantum stuff, my quantum dynamics, and which is why this talk is more about algebra. Kind of simple. Okay, so now I have to get a little bit more formal because now I have to do the actual construction of these maps. I think of the Heisenberg picture of quantum mechanics. I take an algebra of quantum operators, which consists of operators with momenta in them and some matrices, which of course there are some relations between them because of the normal commutation relations between x and p. You all know these. And then you see that if I just reinstate this vector of h bar where it belongs, that my trigonometric Colodro-Sutherland Hamiltonian fits in this exact description, built out of those things. This is an associative but non-commutative algebra. It has a product, but it's not commutative because I have these p's and I have all kinds of matrices hanging around, so this is not commutative. But it does have a Poisson bracket in the sense that I have a bracket, which is a Lie bracket, the commutator, which satisfies the Leibniz rule, which means that it has this, it acts as a derivation on operators. I call this thing a non-commutative Poisson algebra because some people think Poisson algebras must have a commutative product. So I'm just stressing that in this case, my Poisson algebra may be non-commutative in that sense. Okay, now I want to consider what to do as a classical limit. So if I just send h bar to 0, then actually in this previous Hamiltonian, you see that if I do that, I don't have any spins. So that seems too boring. I want to keep my spins. I want to get a spin chain at the end. So this is too easy. And what I could also, the other problem that I get is that if I take h bar to 0, is that my lowest order still contains matrices. And matrices don't commute. And actually, there's a very general result that says that if I want a Poisson bracket on a non-commutative algebra, it will be a commutator. And this is not classical physics either. So I have to be cleverer yet again. Or rather, Mikhailov and Van Haken were cleverer, and they considered this picture a couple of years ago. So I consider Heisenberg equation of motion. I scaled away the I. It's not going to be very relevant. And in this picture, I want to think of it as a set of Hamiltonians, which in this case is just the full algebra, and they act on operators, and in this way they drive the time evolution in the Heisenberg picture. So I have all of my operators, I have this action, and then I have a set of Hamiltonians. And in a normal interpretation, all of these two systems are the same. But that doesn't have to be the case. There's really no reason why you can't just consider a different set of Hamiltonians with a special action that acts on these operators. Really, that's the only observation that these guys had, and well, it's a really good idea actually, and we'll see that it will bring exactly all the results that we want. So how do I do this? How do I obtain classical limits? So first I have to do a little bit of deformation quantization, kind of ordering my algebra a bit better. So I normal order the algebra in such a way that rather than thinking of it like that, I think of it like a normal ordering where now I have functions of x and p, but they may be matrix valued functions, and then formal power series in h bar. So my elements look a little bit like this, and then sums of these things. But this comes with a cost. I now have a star product and a star commutator on this algebra. This is all standard stuff. I basically take the product that I had on the left, and if I want to compute products on the right, I take two elements, I bring them back, compute the product, bring them back. This is all that's there. But the crucial thing is that for the bracket, this star bracket over here, it looks fine as a star commutator, but if I start expanding it in h bar, I get all kinds of different contributions. I get a commutator, then I get a Poisson bracket, then I get a second Poisson bracket, and this in principle goes on indefinitely. So practically, you could think this is quite complicated. So how do I do classical limits? This goes to quotients. I have to do an algebra quotient of this thing. If you've done group theory, which I guess this audience, I assume you have at some point computed a coset of something. You know that the group that you're quotienting by has to have special properties. But once you have these special properties, the result is going to be, again, a group. So for algebras, there's a similar statement. If I have an algebra, and if I mod it out by a so-called Poisson ideal, I'm left with another Poisson algebra. And this I can do explicitly in such a way that the resulting algebra inherits this Poisson bracket already from the first level. And actually, this is a very simple computation. I just take two elements, I bring them back to my original algebra, I compute what the bracket was, and then I just mod out by all the stuff that I want to quotient by. Actually, very simple computation. And in this case, because I took generic elements, I'm left with the commutator. So in this case, the classical limit of this algebra is going to be just matrix valued functions with normal matrix multiplication and, unfortunately, the commutator. Now, this is fine for my normal operators, but it's exactly the problematic case that I talked about before. I want to do something a little bit nicer. And maybe, already to say this here, this kind of quotienting is good because it's a Poisson homomorphism. So this actually satisfies this property that I want a lot of control over what happens between different steps in this procedure. Okay, so to overcome the fact that I have this non-trivial commutator, I can just consider a subset of my operators. And the simplest guess you can make, basically, is saying that I want my operators to be at lowest order elements that commute with everything else. They live in the center. And then at first order, they can be whatever again. And this is precisely what you need, so that at the end of the day, if I compute star commutators of these two elements, I get something that's at least order h bar. Now my commutator vanishes, and I get order h bar. And my elements, concretely, you can think of them as functions multiplying the identity matrix plus h bar times matrix valued function of everything. And this set I call my Hamiltonians. And they act on all these other operators in this normal ordered algebra. I can again do a classical limit by doing this quotient. Same procedure, just a little bit more difficult. When I say more difficult, it's really not that complicated. You should really read the paper by Michailov and Van Haak and just try it yourself. It's really, really nice. The end result is something that looks a little bit odd, maybe. I get H0 as an algebra, which at lowest order just contains functions of x and p, multiplying the identity matrix, plus some correction at order h bar. So my elements are still of the form z plus h bar h. And in the mod, there's this mod going on, which I indicate by this bar. And in the same way as before, I have a Poisson bracket, which it looks a little bit more difficult, but I get something very nice. Now, to I can do the same thing to the action that I already had. So the way that I want to, of course, think about about Hamiltonians that act on operators that then drive some motion. And this I can do again, and I end up with this funny looking new bracket. You see that basically what's happened is that I get a hybrid dynamical system. I get that on the right-hand side, the action of this new algebra on the right-hand side of my equation of motion is partially classical and partially quantum. And in this concrete example, if I take an element from this algebra, my classical piece Z is going to be this part of my Colosio-Sutherland Hamiltonian, which is a scalar Hamiltonian. And then the quantum piece is something that already starts to look a lot like a spin chain. And actually, there maybe as a nice comment for this audience, you can geometrize this picture actually by thinking about it as a vector bundle over a symplectic manifold. You should read Lyashik Reshetich and Sechin for that. Also very nice. All right. So now, if I want to actually end up with a spin chain, I need to be a bit more integrability minded. So I needed to take a set of commuting Hamiltonians, and then I can consider what happens to them in the quotient. So if I go to this hybrid setting, but because they were commuting, they still commute after doing this. So I get this identity for these Hamiltonians. Of course, I write them in the same form as before. And now I can try to freeze them. So I look at a classical equilibrium of all of these Hamiltonians at the same time, but only the classical part, so only the Z ends. I can find those, and then I can just define an evaluation map by saying everything that depends on X and P, I evaluate at this equilibrium. And assuming that this deformation is flat, which is a bit of a technical assumption, this means that this first term drops out. The fact that I evaluate on an equilibrium means that the second and the third term drop out, and I'm left with the final term, which has to be 0. So I find that these two evaluated quantum pieces are commuting Hamiltonians. And if you check what happens, this is just commutativity of spin chain Hamiltonians. So to summarize, I have this commutative diagram, which is quite nice. On the left-hand side, I have Poisson homomorphisms that take my complicated structure and it boils it down from a quantum many-body system with spins all the way to a quantum spin chain. And in the middle, I got this interesting-looking hybrid system. All right, but this actually works. You can check it for basically every single example that I know of. In the cases where we have a lot of structure, you can use it to actually transport all this structure down. In the cases where we don't have the structure yet, we can at least already show that commutativity of the Hamiltonians can go through. That's exactly what these maps are for. And the conjecture, of course, that this works for every single quantum many-body system with spins. There's really no reason why it shouldn't. So to summarize, I have shown you that elliptic integrability is a bridge between these two different worlds of integrability. And if I want to understand this bridge, I need to be able to freeze my things on the long range side down to a spin chain so that I can get this direct comparison. I've shown you that once I freeze my quantum many-body system, I get this hybrid dynamical system, which is quite interesting. And more particularly for my own purposes, I've managed to construct a map, a Poisson homomorphism, that transports integrability from the top to the bottom. Now, of course, now the question you should ask is, what can you freeze? Well, I think you can freeze quite a lot of different things. You can freeze anything that has a parameter in it that kind of obeys the same properties. For example, an R matrix like that can be frozen in the same way. You can try to go from spin to spinless. Maybe you can look at matrix extensions of W algebras, completely random example. Or you can look at spinning gravitational waves, which are things that people in Berlin really like. And then I invite you to think about other things. Do you have systems with multiple degrees of freedom with a parameter that kind of look a little bit separated? This construction could immediately apply to you. And for this, and then finally for future work, maybe to start with the last bit, you can, of course, what I want to do is identify what is the actual integrability underlying all of these complicated long-range systems, freeze it, and by that unifying both the short and long-range realms of integrability. But maybe for this particular audience, the first step is maybe the first bullet point is also very interesting. There's a very nice paper already from over 20 years ago by Cattaneo and Felder, where they showed that deformation quantization for commutative Poisson algebras can be thought of as a topological quantum field theory on the disk, where you get where the deformation is basically thought of as being some kind of path integral over the sigma model, with the sigma model action in the exponent. And it would be very natural to imagine how this would extend now to non-commutative Poisson algebras. So what I really hope is that there will be a new IDD very soon in which one of you is going to tell me how to do this for the matrix case. Thanks.
Yeah, thank you very much for your talk, Rob. So, and also for staying perfectly in time. So we have enough time for questions.
Thanks for the nice talk. You mentioned at some point some result about every Poisson bracket coming from being a commutator of a product. Is it always like the product which also define the associative algebra, or in general it can be different?
That is the product that defines the associative algebra, yes. There
Okay,
is a technical assumption on the algebra that I forgot, but it is quite a generic statement.
Okay, and so does everything like your hybrid things do they always come from something which is just the standard associative algebra with its standard commutator, and then I kind of take a limit where I freeze part of it but not everything, or?
Every example that I know of, yes. There's quite a strong constraint in the fact that the Lie bracket has to be a derivation with respect to that particular product. There are other examples, but that severely restricts your options.
Okay, thanks.
Hi, thanks for the very nice talk. And I apologize, this might be a slightly vague question, but given that in the classical limit you retain some non-commutativity, is there some non-commutative geometric interpretation, but like classical non-commutative geometric interpretation?
Honestly, apart from this geometric picture as a vector bundle over a symplectic manifold, I'm not sure there's much more here. So I'm not sure if I can say much more than that, to be honest. It depends on where your R matrices come in the end. This is the limits that I'm taking are in some sense they are a little bit inspired by these kinds of expansions. I think you could think about doing this kind of construction for non-commutative geometry, but not necessarily with quantum many-body systems in mind.
Okay, any further questions? If not,